Okay, we're moving on to take everything we've got into account and beginning to understand the whole circulation of the Earth. So we're going to talk the Earth's planetary circulation. What is that and how does it relate to our weather? Well, we're going to look at some of the principal features that it has, and then we're going to start scaling this back into our local weather, but that's more next week. So say the Earth didn't rotate. What you would have is one side that was constantly sunlit, and because the equator gets the most sun, that would be where the temperatures got the warmest, and they would rise there, and then they would sink on the other side of the Earth where it was the coldest. But we have a rotating Earth, so we don't have that issue. And because it rotates, what happens is we have several distinct areas of low and high pressure. So you'll notice that right around 30 degrees north, winds kind of spread away from that area. That is where high pressure is actually building into. Low pressure is up around 60 degrees north, and the intertropical convergence zone down around the equator is low pressure. So you can see that plotted on the map right here. So let's go back one here. This is a global pattern. If you were to average out highs and low pressures that you see in January, you would have high pressure sitting over the middle of the Atlantic, low pressure up over Greenland, high pressure over Siberia, more high pressure out to the west, and another low up near Alaska. This is January. Notice when you go to July, these highs slip a little bit further north. The lows aren't as impressive. As a matter of fact, there's not even a high pressure over Siberia at that time. It's more of a low pressure. So there is a change during the seasons and how the global pattern sets up. So along 30 degrees north and south, there's basically an anticyclone. And then up towards the poles, around 60 degrees north, there's subpolar lows. The Aleutian low over the North Pacific, or the Icelandic low. And south of these are fronts. And right over the top of the poles is what they call the polar vortex. We hear that discussed more and more because it can lead to very pronounced, very Arctic air masses getting into the United States. So you think about it, right on the poles, there's no sunshine during the winter. It's getting really cold. The pressure is relatively low aloft there so that it continually just circulates right there. And when that does that, it keeps that cold Arctic air trapped right in that circulation. But when that circulation begins to weaken, then all of a sudden some of that Arctic air can come into the United States. In between, in the mid-latitudes, we have a wavy westerly weather pattern. Ridge, high, winds aloft. And guess what? With the tropopause, we already know that the warmer it is, the further up in the atmosphere the tropopause is. Well, over the tropics, you don't get many fronts through, or almost none down there, so the tropopause can be pretty high. Over the Arctic, it's almost always bitter cold. Tropopause is pretty low. But in between, the tropopause can go up and down a lot across our area. Down across where the tropics are, you get a trade wind inversion where the trade winds are. And it can really change the way weather maritime layers look. Also, you have the intertropical convergence zone. The intertropical convergence zone does not move very far over the oceans. It moves a little bit. And remember, the oceans take a lot of heat to warm them up in the summertime. The same way they don't release heat very fast in the winter. So there's very little motion over the water. However, land, whole different story. They can heat very quickly. So you can see intertropical convergence zones well down south in January. south of the southern part of the Indian Ocean, and guess what? It goes all the way north of India in July. That has major implications for the weather in that part of the world. And here you can see it with the monsoons. During the wintertime, tropical convergence zones well south, you have northerly winds coming out of Siberia. Guess what? There's not a lot of water up there. It's very dry. Exactly the opposite in the summertime. So once that intertropical convergence zone moves back north during the summer, they get wet monsoon flow off the water. And both of these are monsoons. One's just a dry monsoon and one's a wet monsoon. Now, around these planetary highs that are over the oceans, what happens? Well, think about it. If you're on the west coast, your winds are coming across and going down towards the south. So you're bringing in colder air, really, along the west coast, along the ocean. And with that, the ocean is getting colder because it's coming out of the north. Well, the colder the air and the colder the ocean might be, the less chance for convection. So you wind up with San Diego and places like that being relatively dry when the high is situated over them. However, on the other side, on the east coast of the United States, and by consequence, places like Japan or Australia would be towards the other side of the high. They would be more humid, more unstable, and more rainfall. These highs are such a permanent feature that they actually impact global circulations of the oceans. You can see here something called the North Atlantic Gyre. The Gulf Stream flows up on the west side of that. And when it does that, it flows up along the east coast. It keeps the east coast of the United States warmer. And it continues on up across parts of England there and all. So it actually has a warming effect on England. This high that we have sitting out here, the North Atlantic high, causes this at North Atlantic Gyre. And the same holds in the Pacific. And you can see the California curve coming down from the north. Guess what? It gets cold water down there, so it stays fairly cold. There is another monsoon, actually one over the North America monsoon. You have mountains in Mexico, fairly high elevations in the western part of Mexico that heat up. When they get very warm, they begin to form low pressure at the surface. We have convergence of air into that low pressure. And because the low pressure is formed through heating, you actually wind up with a high pressure aloft. So that kind of means that low is just sitting there. What that develops is a very large circulation of moisture coming in from the Gulf of Mexico and partly up from the Southwest Pacific, I guess, and into that part of the United States. And they get lots of rain down in Arizona, New Mexico, even up into southern Utah from the monsoons during the summertime. Okay, when we look at long waves being, well, let's just show you. This makes more sense to me. Look at it this way. There are long wave jet streams in the atmosphere that you can see. Here is a jet across the Atlantic, all of the Pacific. Very horizontal, very straight. But you'll notice it goes down just on the west side of the Pacific and go down on the east side of the Pacific. They are Rossby waves. They're long waves. There's another over here, over the North Atlantic is another area of low pressure. Another one over Europe. There's about 3 or 4 of these across the globe right now, probably 4. Now, there are little troughs that develop in here. There might be one in here, probably another one back in here, another one in here, that flow through these short waves are called these long Rossby waves. But the Rossby waves are these big features. So with that, here is your flow pattern. I talked about a zonal flow over the Pacific where winds are generally coming from the west to the east. But you can get the Mariana flow where you have very strong north winds pushing a lot of cold air south, very strong southerly winds, a lot of cold air north. You get very strong temperature contrast. And these are when you get your biggest low pressure systems, when you have very intense lows. There are also blocking patterns that occur. There probably is one now just east of the United States across Greenland. It's kind of keeping blocked the circulations to the west because it's just flowing around the south. The main jet stream might actually be further to the north, but you have this big area of cold temperatures aloft and circulation. So you get blocks, and when they occur, they tend to put fronts in the same position. They don't move a whole lot, and they can lead to very substantial rainfalls. And some places get very beautiful weather for a long and drought. And you can see the changes in precipitation from that. Jet streams are where the temperature contrast is greatest. Well, that actually occurs further up in the atmosphere, and it occurs right about where the tropopause is, just a little bit below that. Because once you get above the tropopause, you actually get warmer. So just below that, there can be very extreme temperature gradients, and that is where the jet stream forms. And the jet streams move depending on what time of year. In the summertime, they tend to be further north. They're up closer to the North Pole. In the wintertime, they're further south. So right now we're in fall, and we're kind of transitioning from the northern jet stream to a southern jet stream. Cyclones typically develop. We can look at a wave in the atmosphere, very strong winds coming in here and here around the trough, but the winds speed up typically on the east side of the trough. So that is where the speed divergence occurs. We get divergence aloft. If you have divergence aloft, guess what? You're going to get low pressure at the surface. So that is why a lot of times lows are to the east of these upper level troughs. And you can see that depicted here, and highs are to the west side. And here you can actually see the core cut right across the jet stream. Divergence is in the front left quadrant and the right rear quadrant typically. Convergence is in the other two quadrants. There are some other global circulations, El Nino, La Nina. We are heading into we actually are in a La Nina. This circulation is a combination of the atmosphere and the ocean. It cannot be just one or the other. They interact with each other. So with that, let's go back here again, because here is El Nino going on right now. Here is the current ocean cold water. These are temperatures below normal temperatures right now by depth. And what you're seeing here, there's a lot of cold ocean water deep down in the eastern half of the Pacific Ocean. Well, that is reflected in Nino anomalies, and the eastern half is Nino 3, 3.4. 3.4 is the one they typically use, and you can see we're averaging almost 1 degree below normal. For La Nina, you got to average 1 degree below normal for 3 months consecutively, but we definitely seem to be heading that way. So where we transition to neutral, we are definitely transitioning back to La Nina right now. La Nina impact for the United States is it shifts the jet stream. If you go back and look at this jet stream, what it does, instead of the jet stream coming in further south in California, it stays further north. So you wind up with a lot of storms coming in to the Pacific Northwest, riding quickly along the northern half of the country. You don't tend to get the deep trough on the eastern part of the United States that we would get, where very strong nor'easters might form in the wintertime. But it has happened in the past. So this is no guarantee that it's going to stay this way all winter, but this is more typical for La Nina. Another area with this, and we'll go back there. You can see all the different La Ninas and El Ninas, how they fall in line here. One of the things that happens too with water, same impact with the Coriolis effect. So if you have winds from the south, we'll say along Cape Hatteras, and you begin to move the water, the Gulf Stream is moving north along there, what happens is the water tends to get pulled more and more to the right. So it literally makes a spiral down towards the bottom of the ocean. And it pushes the cold water up along the coast and sends the warm water out away from the coast. When these occur, I have seen Hatteras' temperature go from 80 some degrees one day to in the 50s the next. And I know people that have got in the water and jumped right back out because of that occurring. And you can see here the different El Nino phases and La Nina phases and what the impact. North Atlantic oscillation is another one. It's a seesaw variation in air pressure between the subtropical or Atlantic high and the low that's typically over Iceland. When one is stronger than the other, normally it changes the flow pattern across the eastern half of the United States. And this can impact greatly whether we get precipitation and how cold the air is. And you can see here a positive NAO, storm tracks are a little further, a little colder. A negative NAO, we get more nor'easters. And you can see, one of the toughest things to do in the wintertime is forecasting the North Atlantic oscillation, because when we get it right, we can make a major impact on how the winter is going to occur. The Arctic oscillation is another form. It is the one where you have very strong circulation around the poles, and the North Pole, if it continues strong, tends to keep the very cold air further north. When it begins to weaken, it allows more of the cold air, like it did last winter in Texas and Oklahoma, where it came down in the Midwest. At that moment in time, the oscillation had weakened significantly. So I think that is about it. I was going to show you a couple quickie things here on the North Atlantic oscillation and stuff, but here is just what it's phasing through with time. So if you have any questions, please don't hesitate to ask.